morning, students. Let's start today. Today's session, crash course day 9 plus. 9 plus means is we could not finish the topic in one day, so we have to extend it, right? So 9 plus, and which was the topic? Fluid mechanics. As I told you, it's very big topic. Okay, but maximum questions that we expect in this topic is 2 only. So, but anyhow, we have finished it fully. Easy topic, but very lengthy, right? Okay. So what we have to do, where we stopped yesterday? We stopped it at graph of terminal velocity and time. That we had to study. Terminal velocity we discussed yesterday. Okay. So how is the graph? Let's see. Start from here. So if you are going to make a graph, and what happens actually in this one, we know that we are talking about terminal velocity, and terminal velocity we are talking about spherical particle which is falling in the fluid. It may be falling from the rest. Let's say what I am going to make is from the rest. So when it's falling from the rest, initially gravitation force and buoyancy force and viscous force, all three are acting. But here gravitation force is more. So the drop is going to accelerate, or spherical body is going to accelerate. Its velocity keeps on increasing, right? And viscous force also keeps on increasing because it's dependent on velocity. Finally, what happens? Your viscous force becomes such that the total force on that drop becomes zero. That means acceleration becomes zero, velocity becomes constant. And that velocity only we are calling as terminal velocity. Okay. So here we are putting terminal velocity and here is time. So what is happening? What is happening? Velocity keeps on increasing. Finally, velocity become constant. That is terminal velocity. So here terminal velocity I should not make. I will be making here velocity only. Velocity. And here we will say this is terminal velocity. Okay. This is terminal velocity. So it start from 0 and here it's going to increase and it will become like this. This is the graph of velocity with time. And here this is terminal velocity. This I have made for a single drop. Okay. Started from 0, velocity keeps on increasing and finally it became constant. Okay. Right. Right then. Based on this one question we will see. What is this? Two spherical balls are here. Its radius is 2 mm, its radius is 1 mm, its density is rho 1, its density is rho 2, where rho 1 is equal to 8 rho 2, and masses are same. Okay, so both spherical balls are falling from rest in a liquid of coefficient of viscosity eta and density 0.1 rho 2. That means density of the liquid is 0.1. Find ratio of the terminal velocities. Okay, so terminal velocities formula we derived yesterday. What was terminal velocity formula? It was 2 by 9 eta r square g. Okay, rho minus sigma. Rho was density of the particle and sigma was the density of the liquid. Okay, now we can directly put it, nothing much is there, we'll directly put it into ratio. Okay, so velocity of T1 we will say for the drop 1 and this is for drop 2, right? So 2 by 9 eta, it's common. So in this one nothing we have to do, this is going to cancel. Okay, then R1 square here, okay, here R2 square, then G is going to cancel anyhow, G by G. Then what? Rho 1 minus sigma by rho 2 minus sigma. Correct? You have written everything. G is gone, this 2 by 9 eta is gone, so I am not repeating it. What do we have? R1 square by R2 square and rho 1 minus sigma by rho 2 minus sigma. Okay, that's it. Right. So R1 square is 2 mm. So 2 mm means its square is 4 mm square. This is 1 only. Okay. So 4 by 1. Now mm square by mm square. So I don't have to think about the units as such here. So 4 by 1. Then what we have? Rho 1 minus sigma. So rho 1. This is rho 1. But rho 1 is actually given as 8 rho 2. Okay, right, 8 rho 2 minus sigma is what? 0.1 rho 2. Okay, then rho 2. Rho 2 is rho 2 only. So rho 2 minus 0.1 rho 2. That's it. So what we got? This is 4. 8 minus 0.1, that will be 7.9. 7.9 rho 2 and 1 minus 0.1, that means 0.9. Rho 2 cancel. So 4 into 7.9 by 0.9, that is 4 into 79 by 9. Approximately, if we calculate, we are around 36, 35 and 36. Okay, 35 to 36. Right, 35 to 36 will be our answer. So this is on terminal velocity, right? Based on the formula. Next is what? Viscous force between two layers of liquid. Now, we already have discussed that there is something viscous force whenever a spherical body is going to drop in a fluid. Fluid offers a viscous force, right? Or opposition to the flow of that spherical body. But then, now this viscous force is between two layers of liquid. There it was not between two layers. As I said, one spherical body is moving in the liquid, that is the opposition force offers by liquid to that spherical body. Here, it is the opposition to the relative motion between two layers of the liquid. If the liquid is in motion. Okay, now if the liquid is in motion, we know that the layers of the liquid will be moving with different velocities. The layer which is in touch with the ground, suppose we are talking about a river, okay, the layer which is in contact with the ground will have least velocity, whereas the layer which will be having at the top will have maximum velocity. Reason? Because the ground is offering the resistance to the layer which is in touch with the ground, and ground is at rest, it cannot move, right? So it offers more resistance. Whereas as you are coming up, then what happens? The top layer is in contact with the below layer of liquid only, and that below layer also can move, right? So what happens? Top layer moves with higher velocity, it will drag the lower one also. But dragging means is what? It drags it because the lower layer obviously tries to stick with it. That means it tries to oppose its motion. Like friction, block on block problems. One block you are pulling, other block is also coming with it. We ask that how it is moving because of friction. The same thing happens in liquids also. Correct. So we want to find out what is viscous force between the layers of liquid. So two layers I am making. Let's say first one is the top layer, and this is the bottom layer. Okay, bottom layer is almost at rest. Its velocity is almost zero, whereas this is having certain velocity. And let's say this is D. Okay, so now what will happen after that? If suppose more layers if you make, this layer will be here. Okay, its velocity will be little less, its velocity will be less, its velocity will be even more less. Like this actually, as you are coming down, the velocity of layers keeps on decreasing. Okay, like this. So this length is actually here representing velocity. So as it's moving down, and it's because of the viscosity only. More the viscosity, more will be the fall in velocity. Okay, more will be the fall in velocity. Like suppose you have certain liquids like honey is there. Okay, you will see that there is upper layer if it has certain velocity, then the almost layer will be almost zero. So fall of velocity is huge in honey as compared to water. This is I have tried to make a water. Okay. So then what is viscous force in this case? In this case, viscous force is proportional to rate of fall of velocity with depth. You can say velocity gradient. Okay. Rate of fall of velocity with depth. So delta V by delta Y. Delta V, that means fall in velocity per unit depth. Okay. And this is also proportional to area, because more the area of these layers, more particles will be in contact. Now upper layer, if suppose I make like this, suppose it's like this, okay, this is the area, okay, and the lower one also I'll be making. This I have though told you that this is velocity actually, but let's assume that. Okay. So what will happen in these two? There will be particles over here. They will be in contact. Okay. So bigger the surface area of these layers is, more particles will be in contact. More particles will be in contact means more opposition will be there. So force is proportional to delta V by delta Y. At the same time, force is proportional to area. Let's combine them. So F is proportional to A delta V by delta Y. Now this delta V by delta Y is actually negative. Why? Because as you are coming down, velocity is decreasing. So delta V will be negative. So we'll put minus here. Remove this proportionality. You get eta A delta V by delta Y. Okay, minus here. Or normally we write it as minus eta A dV by dy. Okay, now coefficient of viscosity, we didn't talk about its unit, right? What is its unit? Its unit is poise. CGS unit is poise. Okay, CGS unit is poise and SI decapoise. Decapoise means 10 into poise. Okay, dimensions we can write, but dimensions we can write from here also, we can write from 6 pi eta RV also. Okay, so if suppose 6 pi eta RV use, 6 pi eta RV. Now 6 pi is anyhow constant. So its dimensions are M, L, T minus 2. Okay, eta's dimensions we want. R dimension is L, V dimension is LT minus 1. Okay, so what we are getting? Eta's dimensions are, only one M is there, so M. Here is L, here is L square, so L minus 1. Okay, here is T minus 2 by T minus 1, so T minus 1. So dimensions are M, L minus 1, T minus 1. Okay, so new formula we got one for viscous force between the layers of liquids, and this is the dimensions, right? Okay, then what we have? Okay, any questions can we solve on this one? Eta A dV by dy. We can solve. Okay, we can solve if you want, or a direct formula. Direct. Okay, we will see that. We will see that question later if we can take. Okay, let's move ahead. So now what we have? Fluid dynamics. So far what we were discussing, in that one, fluid was at rest, except the last thing in which we found that what is the viscous force between the two layers of liquid which had certain relative motion. That means it was flowing. Before that, we were talking about fluid at rest. Now we are talking about fluid dynamics. That means fluid is in motion. Fluid is in motion. Okay. Now fluid is in motion means what are going to happen? Three properties of liquid that we have discussed so far: density, pressure, and now we are talking about velocity because it's in motion. Right. So we'll talk about three properties in when the fluid is in motion. Okay. What we have now? Types of flow. Two types of flow, or rather we are going to study mainly one type of flow which we call as steady flow. Okay. Steady, which is also known as streamline or laminar. Streamline or laminar. Okay, now what this steady flow or streamline or laminar flow is? One thing is there, if we talk about, let's say, we take an example of a pipe. Okay, we make a pipe here. Okay, let's say make it like this. This is the pipe. Okay, and in this one, liquid is flowing. So at any point you take, maybe this point here, maybe this point here, maybe this point here. Okay. So at these points, whatever particles are reaching, because if suppose the liquid is flowing like this, so whatever particles are reaching here, okay, at this cross section, here and here, okay, A, B and C. Whatever particles are coming, the particles pressure, particles density and velocity. Normally when we talk about particles, we will associate only velocity there. Okay. So velocity at point A for all the particles which are coming will be same. Particles of, or rather velocity of all the particles which are reaching at B will be same. Particles velocity here at C also will be same. Am I saying VA equal to VB equal to VC? No, I am not saying that. I am not saying VA equal to VB equal to VC. Okay, but what I am saying is, whichever particle is reaching at A, their velocity will be same. Whichever particle is reaching at B, their velocity will be same. Here also velocity will be same. That means with the time, the velocity of particles which are reaching at A, which are reaching at B, which are reaching at C will be constant. This is not equal, but here whatever will be velocity, that is constant. At section A, velocity of particles is constant. Same way at section B, same way at section C. Okay, because different particles are coming, so it's a flow. But at A, if you are going to put measurement, if you are going to do the measurement, you will find that they will have same velocity. Different meters if you are going to put over here. VB will show you always constant, VC will show you always constant, VA will show you always constant. Okay. Other than that, if suppose that this is pipe, some kind of a pipe this is, then in steady flow, the particles which are in contact with the pipe here, if I can make it with a different color, okay, these particles here which are in touch with the pipe, okay, they are almost at rest here, or you can say at rest, not almost, they are at rest. Okay, these are at rest. And which one? Steady flow or streamlined flow or laminar flow. Right, this is steady flow. Then second one we are going for turbulent. In between is unsteady flow. Okay, what is turbulent now? Turbulent means is in which velocity of all the particles, suppose at section A we are talking, it's not constant. Even direction is also not constant, magnitude is also not constant. This particle will have something else, this particle will have something else, this particle will have something else, and the particle which is following this will have something else. That's turbulent. Too much flow is there, then it is called turbulent flow. Okay, now let's see turbulent. If you have to write, where shall I put turbulent here? This next one I have given for this one. Okay, so turbulent. Okay, this will remove. This will. Okay, so turbulent. Okay, what is that? Where there is flow is very high. Flow of liquid is very high. So in this one, what happens? The velocity of particles at any section is not constant. Any section is not constant with time. Okay. And second thing that I told you for steady flow, that is the particle which are in contact with the pipe are at rest in steady flow. Here they are not at rest. Okay. Particles in contact with pipe are not at rest. Okay, and liquid's pressure and density also keeps on changing. Like in steady flow, I said pressure here. Okay, if you're going to take it unit volume or unit area, so that we can define pressure and density. Here, pressure and density are constant. Here, pressure and density remains constant. Here, pressure and density remain constant. But in turbulent flow, neither pressure is constant, nor density, nor velocity. Okay, right? Okay. So now Reynolds number is there. Reynolds number is what? A number through which we define that whether the particular flow is steady flow or unsteady flow or turbulent flow. So Reynolds number, before defining Reynolds number, we have to talk about two forces. Okay, what are two forces? The two forces are there. One is viscous force. Okay, one is viscous force. We have discussed it already. Eta A dV by dy. And another one is inertial force. Inertial force in liquids. Yes, obviously, because liquids also have mass. The inertial force will be there. And this inertial force we studied in laws of motion also, and we called that as thrust force, if you remember. Okay, it was something like V into dm by dt. Like force is what? Rate of change of momentum. Then we said that if mass is constant and velocity changes, then force is this. But if mass is constant, okay, and velocity changes, it's m dv by dt, right? So this is v dm by dt. And on this one, we did one question also. There is a water gun through which, right? Same thing, water gun only. So this is v into dm by dt. This we are calling as inertial force. Okay, this is v dm by dt, and this one eta a dv by dy. Okay, now ratio of these two is only Reynolds number. This is Reynolds number. We'll say this is actually inertial force by viscous force. Okay, now this inertial force, this Fi, which is V dm by dt, this is mass, this is mass. Mass I can write as density into volume also, right? Because we are talking terms of liquid. So V into d by dt of rho into volume. V is volume here, not velocity. Okay, so this is volume. Now density, if I assume density is constant, so rho into V, now it becomes dV by dt. Now dV by dt is what? If I are talking about a pipe, let's say, there is a pipe here. Okay, pipe's area is A. Okay, pipe's area is A. dV by dt will be rate of flow of volume. Okay, so if its area is A, and suppose per unit time, okay, this liquid of ours, this is liquid. Okay, liquid. Okay, frame if I can. All right. Okay, so this is liquid. So this liquid is suppose is moving x. Is moving x here. So what we can do? This we can write as rho into V into volume. This is so d by dt into area into x. Area also constant. Take it outside. Rho VA. Dx by dt becomes velocity again. So this becomes rho AV square. Okay, inertial force here is rho AV square. So let's bring it over here. Say Reynolds number. Reynolds number is what? Let's see. Okay, so I am putting it here rho A V square. Why? Because inertial force by viscous force. Now we have to put eta A dV by dy also. Now we have to define what it is. Okay. So first assume that these are the two layers that you are talking. Okay. So velocity is V. This velocity we are taking as Z. And this is, let's say, D. Okay. So rho A V square. So its area also you have taken. Okay. Area is A. This area is A. Or area in contact is A. Area in contact is A. Because here we have taken already D. Okay. This is D. So if suppose that this is circular, then its area is already we have taken, right? So we are not talking about this is A. Area is this one. This is A. Okay. Right. So now rho A V square. Okay. Then into eta A dV by dy. Now dV means difference between here and here. So what is difference? V by y. What is y? D. So A and V cancelled. So what we got? Rho V D by eta. This is the formula of Reynolds number. Okay. Now Reynolds number says if this Reynolds number is less than 1000, it's steady flow. Okay. And if this Reynolds number is greater than 2000, it's turbulent. And if it is in between, it's unsteady. Okay. That is Reynolds number is less than 2000 and greater than 1000. Then it is unsteady. But we don't have to do much with these two. Okay. Maximum we are going to talk about steady flow only. Alright. So this is steady flow. Fine. Now we are going to talk about equation of continuity. Now equation of continuity is what? Equation of continuity is based on conservation of mass. Okay. It is talking about the flow of liquid through a pipe. Okay. So what it is? We say take a pipe, let's say. Okay. Of variable cross sections if we want to take, we can take variable cross section also. So how to make it? Okay. Like this I am making. Okay, it's like this. Suppose its area here is A1 and its area here is A2. Variable. Okay. Now, in this one, this pipe is such that it is neither holding the water or liquid nor there is any leakage. Okay. Neither it can store nor there is leakage. Pipe can't store the water and there is no leakage either. There is no leakage either. Okay. So what will happen? Whatever water goes inside, same has to come outside. There is no other way because pipe cannot hold it and there is no leakage either. Okay. So the mass which is going, same mass has to come out. That's why we call it as it is based on conservation of mass. Okay. So equation of continuity is based on what? Conservation of mass. Okay. It's based on conservation of mass. Okay, fine. Are we talking about steady flow? Yes. Whatever we are going to study is all about steady flow. So steady flow means is density same here and here. Yes. Okay. So when we say mass flow is same, density is already we have said same. So that means volume flow rate will be same. Because dm by dt is what? d by dt of density into volume. And density we are saying is constant. So what it becomes? dV by dt. What is that? Volume flow rate. And volume flow rate is what? Area into velocity. A into dx by dt. This is only volume flow rate. What is volume flow rate? Area into velocity. Volume flow rate. Okay, in equation of continuity what we have? dm1 by dt, here is mass which is entering per unit time, is equal to dm2 by dt. Okay, and dm by dt is what? Area into velocity. So what we can say? A1 V1 equal to A2 V2. Okay, what we can say? A1 V1 equal to A2 V2. That is only our equation of continuity. A1 V1 equal to A2 V2. Okay, this is equation of continuity. Okay, let's see further what it is. Okay, there is question on that. So here area we can see is 6 meters square. Here we can see 2 meters square, and we want to see what is volume flow. But velocity I have not mentioned in this one. So let's take velocity. Suppose velocity here is 2 meter per second. Okay, so find volume flow rate and mass flow rate. Okay, so first of all here let's find out what is the velocity. Okay, so first if we want to find velocity over here, we are applying equation of continuity. Equation of continuity says us A1 V1 equal to A2 V2. A1 is what? 6, V1 is 2, and here is area is 2, so velocity. So velocity is coming 6. Okay, then volume flow rate. Now volume flow rate is A1 V1 only. Okay, so volume flow rate means dV by dt. So dV by dt is actually area into velocity. And what is this? 2 into 6, 12. So 12 meter cube per second. Okay, area is unit meter square, velocity is in meter per second, meter cube per second. Then mass flow rate. When you say mass flow rate means dm by dt. dm by dt. What is that? That is rho into dv by dt. Okay, so if this is water, we say that this is water is here flowing. Water's density is what? 1000 kg per meter cube. Okay, so we'll multiply here. dv by dt you already have found. So this is 1000 into 12. So we'll say that 12,000 kg per second is the liquid flowing. This is mass flow rate. Okay, this is mass flow rate. Just a moment, a break of a minute. Okay, let's move ahead then. Now what we have next, another question is there. So here there is a pipe. Okay, the pipe is like this, which is divided into two sections over here. Here its area is A, speed is 3 meter per second. Here is also area A, speed is 1.5. Here area is 1.5A, and velocity is asked from us. So same conservation of mass only. Mass flow rate from here equal to mass flow rate from here plus mass flow rate from here. Okay, or volume flow rate from here equal to volume flow rate here plus volume flow rate here. So what it is, what it will say? A into 3. This is the volume flow rate at the entrance. Then here A into 1.5 plus 1.5A into V. V we have to find. So A in 3A minus 1.5A, that is 1.5A equal to 1.5A into V. This gets cancelled. So V equal to 1. V will be 1 meter per second. Simple. Okay, simple question. All right, next. Okay, one more question is there. A cylindrical tube of spray pump has radius r, other end of which has n fine holes, each of radius small r. If speed of liquid is v, the speed of ejection of liquid through the hole is. Speed of ejection of liquid through the hole is. Okay. What he's trying to say, there is a pipe. Okay. Pipe is having radius r. So this is how the pipe is. Okay. Its radius is r. Okay. This radius is r. Then suppose at this end there is this section, and in this section there are small holes like this, through which the liquid has to go. Question is asking the speed of ejection of liquid through these holes is. Okay. Again, the thing is saying steady flow. Pipe cannot store the not charge. Pipe cannot store the liquid, or there is no leakage either. Okay. So whatever the flow of liquid is, what is the volume flow rate? Same volume flow rate will be from here also. That is it. Nothing else. Okay. So let's find then. So area into velocity. So here it says that its radius is r, and speed of liquid is v. Okay. So A1 V1 equal to A2 A2, nothing else. Okay. So A1 is pi r square, V1 is v. Now this is what? Say n holes are there. So n into their area pi r square into velocity V2. Pi gets cancelled. That's all. Yeah. So V2 equal to Vr square by nr square. Vr square by nr square. That's it. That's V2. Right. Very simple. Next. Okay. Bernoulli's theorem. What is Bernoulli's theorem? Bernoulli's theorem is based on conservation of energy. Based on conservation of energy. Okay. Is it also for the pipe? Yes. Same pipe. Okay, we can make it like different cross sections if we want. Like this it is. Okay, liquid is flowing in this way. Here pressure is P1, here pressure is P2. And even the height we can say, suppose that ground or datum or the reference, we take this is the reference. Okay. So then we can say this is H1 and this is H2. Okay. So what is happening here? The liquid always flows from higher pressure to low pressure. That means we know that P1 is greater than P2. There is no doubt about that. So what's happening? Pressure, the force due to pressure is working. And what we will do? We will apply work energy theorem. So we will say that work done by pressure, force due to pressure, not pressure, work done by force due to pressure, okay, plus work done by gravitation, because you are increasing the level also in the diagram, is equal to change in kinetic energy. Okay. So when we derive it, we are not deriving it here. Okay. But work done, how to write when we are talking about a fluid, gas or a liquid? Okay, it is actually P delta V. Okay, for a particle we used to say F dx or F delta x. Okay, here it is P delta V. That we have to remember. Okay, but in general I am writing Bernoulli's theorem. What is the conclusion? Okay, so it says that energy which is in the form of pressure, potential energy and kinetic energy at any section is constant. That means energy here and energy here will be equal. So how it is done? It is P1 plus rho GH1 plus half rho V1 square. That is the velocity here. Okay. And here velocity. And this, in this one also equation of continuity is valid. Absolutely. This is A2 here, this is A1. So A1 V1 is equal to A2 V2. There is no doubt about that. This is valid. Okay. Right. So P1 plus rho g H1 plus half rho V1 square equal to P2 plus rho g H2 plus half rho V2 square. What is this? This is energy per unit volume. Okay. This is energy density also you can say. Energy per unit volume. Okay. So this form of energy or energy per unit volume in a liquid flowing through a pipe is constant. In which flow? Steady flow. Not in turbulent flow. This is all steady flow. Okay. So this is your Bernoulli theorem. Now, what are its applications? Many applications are there. First application is this. There is a pipe is there, a variable cross section. Okay, steady flow is there in that one. There is steady flow. Okay, maybe here velocity is V1, here velocity will be V2. And he is asking what is relation between pressure. Okay, so if suppose in this one, I assume that because they are at the same level, okay, the same level means potential energy is not changing. Okay, this is the level of center of this cross section of both is same. So potential energy is not changing, I am saying. Okay. So what then? Let's apply Bernoulli's theorem here. This is your section 1 and this is your section 2. So P1 plus half rho V1 square equal to P2 plus half rho V2 square. Okay, now there is one thing given here. Here its area is 5A given, here its area A given. That means we have relation between V1 and V2. Okay, so what it is? 5A into V1 equal to A into V2. So this is getting cancelled. So this relation is there. So can we use it? Yes. Okay. So what we can do? We can find it what is pressure difference because he is saying relate P1 and P2. Okay. Okay, so P1 minus P2 half rho V2 square minus V1 square. Now what is the relation? We know V2 equal to 5V1. Put it here. Half rho is 25V1 square minus V1 square. So half rho 24V1 square. So this is 12. Okay. So P1 minus P2 is 12 rho V1 square. And P1 is greater than P2. We know obviously because flow is like this. The answer is also coming P1 minus P2 is positive. Okay. This way we can apply Bernoulli's theorem to find out the pressure difference at 2 points. Wherever velocity is more, pressure will be less. Here velocity is more. V2 is equal to 5V1. So here pressure is less. Where velocity is less, pressure is more. Okay. Next is what? What is the application? Wing of a plane. What happens in aeroplane? We try and understand the takeoff of aeroplane as well as when it floats. Floats means is when it's reach its maximum height and moves horizontally. That's floating condition. So when it takes off and when it is floating, in both the cases we try to understand the process with the help of Bernoulli's theorem. So what happens in that? When the plane is going very fast, we know that with respect to the plane, air is coming in this direction. If I assume that plane is at rest, then air is coming like this. So air here goes in this direction here, let's say with speed V1, and other one will go straight like this. That's with speed V2. Okay. Now what happens? The same air, this travels this much and reach here, whereas this is moving like this. Okay. Both have to reach at that point the same time. Same time. This also takes t, this also takes t. Now whose velocity is more? Now obviously this is traveling more distance. So V1 will be more than V2. V1 will be more than V2. Now a little while ago I told you, if velocity is more, means pressure is less. So here pressure, which I am saying P1 let's say, and here pressure is P2. So we know that here P2 is greater than P1. When P2 is greater than P1, then what will happen? Obviously, this pressure is going to apply force on this one. If suppose its area is A, then force will be pressure into area. And obviously, it is more than P1A, which is from the top. From here also pressure is there. But since P2A is more than P1A, there is a force upwards, and that balances your mg. Okay. In floating condition, P2 minus P1 into A is mg. Floating condition of plane. But if suppose you have to take off, now in take off you have to create more difference in velocities so that you can lift it up with acceleration A. During takeoff, what will be the condition? During takeoff, okay, now you have to go up with the acceleration A. So what we'll say? P2 minus P1 into A minus mg equal to mass into acceleration with whatever acceleration we are going up. This minus mg equal to ma. Okay, that's for takeoff. So this is wing of a plane, or how takeoff happens and how floating condition of a plane happens. Okay. Then what is there? Torricelli theorem. Okay. Now Torricelli theorem talks about if there is a hole in a container. Suppose this is a container we have. Okay. And in this container we have hole. First of all, let me make the container. Okay. This is our container. Okay, now in this one there is a hole. So here we will make a hole, small hole. Here is a hole. Okay, and this is full with liquid. Okay, this is full with liquid. Right? Like this, it is full with liquid here. Okay. Now what will happen? We all know that it will be water will be going outside because from the hole. So we want to know that with what velocity this water is coming out from here. Okay. This is only done by Torricelli. Okay. So we call it as Torricelli theorem. So what is happening here? Where we have to apply Bernoulli's theorem? We'll apply it to any two sections we can apply, but for our convenience, we take this is our first section and this is second. Both are outside, right? This is also outside, here is also outside. So one thing is clear, here also atmospheric pressure is acting, here also atmospheric pressure is acting. The second thing that we want is, now let's decide what are their heights. Let's assume this is h. Right, and this is small h we can take. Okay, so let's apply Bernoulli's theorem. So first section here, P naught plus rho g h, potential energy, I am considering this to be datum, reference, plus half rho. Now this has to come down. Velocity of this means, with what velocity this is going to come down? So in this velocity is v1. Okay, and one more thing I have to tell you about area. Its area is A and its area is A, and this A is huge as compared to small a, because there is a hole in a container. It has to be very small, right? So half rho into v1 square. Bernoulli's theorem I applied. Here also you apply at section 2, P naught plus rho gh plus half rho v square, and this v only we are calculating. Okay, now I applied equation of continuity. Okay, equation of continuity with whatever, if suppose this is going out, whatever volume goes out, that volume only will come down. No? So volume flow rate is constant only, right? Whatever is volume flow rate here, same is volume flow rate here. Correct or not? Hmm? Correct. So what we can say in this case now, if equation of continuity I apply, say AV1 equal to AV. Now I already said that A is very large as compared to A. That means A by A is huge. Okay. But in this one, we are getting A by A. A by A is equal to V by V1. If A by A is very high, that means V by V1 is also very high. So V is greater than V1. So that means I can say this is negligible as compared to this. V1 is negligible. Negligible as compared to V. Right. So if velocity itself is negligible, then what about kinetic energy? Kinetic energy also will be negligible. So this kinetic energy is negligible. So we can neglect it. Okay, fine. Now we have equated that already. This and this gets cancelled. Okay. So rho g h minus h equal to half rho v square. Rho gets cancelled. So v equal to root 2g h minus h. This is velocity with which liquid will come out from here. Root 2g h minus h. That means it depends on this height. Okay, root 2g h minus h. That is the velocity of efflux. What it is called? Velocity of efflux. Okay, root 2g h minus h. When it will be maximum? When this hole will be in the middle at h by 2. When velocity will be maximum? When the hole will be in the middle. Remember that. Okay, for Vmax, h should be equal to h by 2. Now, many things we can do from here. How the flow will be there? Flow will be there like this. Okay, so can we apply horizontal projectile motion in that? Obviously, you can apply. This will be called as range. And there is time of flight also here. That also we can find. Okay, the range is what? Range is horizontal velocity into time of flight. Horizontal velocity is this velocity of a flux. So velocity of a flux into time of flight. Now what is time of flight? From horizontal projectile motion, that also we can find. The time of flight is root 2h by g. Because here vertical velocity is 0, horizontal projection. So how much down it is coming? H. Have we given any vertical velocity here? No. So it's kind of a free fall, like a free fall, as if you are dropping a particle, right? So what was the time of descent in that? Root 2h by g. So here also, root 2h by g. This is time of flight. So range is root 2g h minus h then into root 2h by g. Both are in square root. Okay, when range will be maximum? When velocity is maximum and with h by 2. Okay, fine. So this is Torricelli theorem. Let's move ahead. Okay, there is a question now. A manometer connected to a closed tap reads 3.5 into 10 to the power 5 Newton per meter square. When tap is open, its reading is 3 into 10 to the power 5 Newton per meter square. Find velocity of flow of water. Alright. Let's see. Okay, two conditions are given. One, when the tap is closed, another one is tap is open. So, in the two conditions, is there any change in the position of the manometer connected? No. Why I am asking? Because in Bernoulli's theorem we are going to use, and Bernoulli's theorem says what? P plus rho gh plus half rho v square is constant. So if position is not changing in two cases that we have, that means rho GH will be same here also, there also. So difference is not there. Okay. So in the first case, what is there? Pressure is 3.5 into 10 to the power 5. Position rho GH. When tap is closed, what is the velocity of the water? Equal to the second case, 3 into 10 to the power 5 plus rho GH, no change in the position, plus, then what? He is asking velocity, half rho V square. Okay, so 3.5 minus 3 into 10 to the power 5, rho GH gone. 0.5 into 10 to the power 5 equal to 1 by 2, density of water into V square. Okay, this is what, 5 into 10 to the power 4. This is 5 into 10 to the power 2 equal to V square. V is 10. Okay, V is 10 meter per second. Right? Okay, let's see. Okay, one more question is there. Simple question. This is velocity of a flux is being asked from us. And this hole actually, let's make it in the bottom. Okay, not this. Yeah. Okay, we'll make it at the bottom. So that we can say that, or we can take directly total height. So from here, what is the velocity? Very easy question. This is full of liquids. Liquid. Okay. So liquid is here. Okay. Liquid is here. Fine. With what velocity? The velocity of flux directly we can do. V equal to root 2 GH. That's all. 2 into 10 into 20. Answer is 20 meter per second. Simple question. Right? Okay. Then, okay. From here also there is a liquid flow. Relation between VA and VB, PA and PB. Now the question here is, first of all, if there is a continuous flow, it's a pipe. Okay, and steady flow is there as usual. So is there any change in the area throughout? The area is constant. Then velocity will be constant because the equation of continuity is valid. Okay, what we can say? V at A into area, V and B, area cancelled, VA equal to VB. There is no doubt about it. Then he says find the relation between PA and PB. So whenever we have to find relation between PA and PB, that means we have to apply what? Bernoulli's theorem. So Bernoulli's theorem, first of all, we have to decide what is the reference. So take this as a reference. Now let's apply. So pressure at B. Since you have taken it as reference here, potential energy is 0 plus half rho VB square equal to, now here, pressure at A. Now potential energy is there here, rho G into what shall we take? H we take, let's say this is H. Okay, so PA plus rho GH plus half rho VA square. Now we already have seen that velocity at A and velocity at B are equal. So that means this and this are same. Okay, so what we can say? Pressure at B minus pressure at A equal to rho GH. Right? This is like this. Okay, let's move ahead then. Okay, one more question is there. A wind with speed 40 blows parallel to the roof of the house. Area of the roof is 250 meters square. Assuming pressure inside is atmospheric pressure. Force exerted by wind on roof. So what it is actually? Suppose this, I am making a roof here, and I am making this is rectangular. Okay, let's try and understand. This is a roof. Wind is blowing. Wind is blowing from the top. Okay, this is wind. This wind is blowing. Okay, from the top with certain speed. A roof area is 250 meters square and speed here is 40 meter per second. Okay. Here they say atmospheric pressure is there. Okay. Then what they want? The force exerted by wind. Now we should know that what is pressure here. Then only we can find out what is the force exerted by wind on roof. Okay. But one thing, as you know, we have discussed before, here velocity is more. Here velocity is zero. Where pressure will be more? This is only more. So if this pressure is more than the pressure here, how will be the force exerted? Upwards. Force will be like this. And what will be that force? Force will be P naught minus P1 into area. Something very similar to that we discussed for wing of the plane. Okay. Alright, let's find now. How to find this P1? Apply Bernoulli's theorem. Here, this is section 1, this is section 2. And there is no change in potential energy because this is just below this roof and this is just above it. Okay. So P1 plus rho GH, if you want to write potential energy also, plus half rho V1 square. Okay. Equal to P2 plus rho GH plus half rho V2 square. Rho GH is gone. Okay. Now P1 is which one? What is we are taking? This is only P1. Okay. This is P2. So P1, okay, plus half rho V1 square equal to P2, which is equal to P naught. It's given its atmospheric pressure plus what 0. Okay, so are we getting here P2 value? Yes, we are getting P2 value or P naught value. What is P naught value? See, P1 plus half rho 40 square. That I am going to put here. Okay, now see. So P2, that is P naught minus P1. So P naught minus P1 is P1 is cancelled. So you are getting half rho into 40 square into area. Area is what? 250. Now this is force. Now what is the density of air? You can consider 1.2 kg per meter cube. Okay. So 1.2 by 2 into 1600 into 250. Huge force is there. 0.6. Okay. 0.6 into 1600. So it will be 960 into 250. That many newtons. Right? So this is how the force acts on the roofs because of the too much wind. Okay, one more question is there. Let's see what it is. A small hole of area 2 mm square is present near bottom of a fully filled tank of height 2 meter. Find rate of flow of water through hole. Rate of flow of water means dV by dt. So that means area into velocity only is asking. Area is given. Yes. And height of this, then nothing is there. It's very simple question. Okay. What question is asking us? dV by dt. And dV by dt is what? Area into velocity. What is this velocity? Velocity of a flux. So area is 2 mm square. 2 into 10 to the power minus 6 meter into velocity of a flux means root 2 gh. So 2g into 2. Okay. So 2 into 10 to the power 6. And here 2 into 2, 4, root 40. Make it as 20 meters so that we can easily solve it, right? This is 20. So now this is root 400. 20 will come out. 2 into 20 into 10 to the power minus 6 meter cube per second. Right? So this is your rate of flow of water. Okay. Surface tension. Last topic of this chapter. Surface tension and surface energy. But before that, we'll take 1 minute break. Right. So surface tension and surface energy. So first let's talk about surface energy here. Okay, what surface energy? So to understand that, what we will do is we will take one container. Okay, take a container first. This is a container. And let's make okay, and take one more. This one will make it the top also. Okay, and in this one liquid is there. Okay, there is liquid in this, but liquid is how will be the liquid? Liquid normally will be like this. Okay, it will be in this way. So the top layer of the liquid will be slightly bent. Reason is, if we are going to see two particles here, liquid particles, one you take here and one you take here. So what happens? This particle here is surrounded by another particle here, 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 here. Whereas this is surrounded by particles in all directions. Okay, so on this one there is force. Which force is the intermolecular attraction force? Okay, intermolecular force, attraction force, which we call it here as cohesive force. Okay, intermolecular, between molecules of same type, cohesive force. Okay, so here force is like this, here force is like this, here force in this way, here force in this way, here force like this, here like this. So this is actually an equilibrium. Equilibrium means is minimum potential energy. Minimum potential energy. Okay, what about this? Let's see. Force here like this, force here like this, force here like this, force here like this, force. Is this in equilibrium? Answer is no. There is a constant force on it, bringing it down. This is not in equilibrium. So if it's not in equilibrium, means its energy is more. So energy is more. Okay, energy is on higher side. Equilibrium means minimum energy. If it's not in equilibrium, means energy is more. So whatever the particles are there on the surface, they all have, in this, if we talk in terms of this one, then they have maximum energy. Okay, all particles on the surface have maximum energy. Okay, that's why surface energy is maximum. That's why we are talking about surface energy. Okay, and because of this, as we are saying that there is a constant force on these particles which are at the top downwards. So because of that, this layer is also not straight. It is curved. So it is curved means it is always in tension. Surface is always in tension because it is stretched. This is what we are calling as surface tension. So it is always curved, the top surface. Yes, it is always curved. Like you can see this drop of water. What is the shape? Spherical. Okay. Bubble is there. Okay. So all these are spherical in shape. Why they are spherical? Because of surface tension. And what surface tension tries to do? It tries to acquire minimum surface area. It has to be in curved, right? So it tries to acquire minimum surface area so that it can have minimum surface energy. It wants to have minimum so that it can be in equilibrium, obviously. Okay. So it tries to acquire minimum surface area. And when it tries to acquire minimum surface area, its shape becomes spherical because sphere has minimum surface area for a given volume. Right? Okay. So surface tension makes them in this one. But let's come back to surface energy at the moment. Surface energy is the energy which is maximum here. Okay. Now, what is surface tension then? What is the relation between surface tension and surface energy? So, surface tension is surface energy by surface area. By surface area. Okay. Now, if suppose we compare, okay, what we compare, I make two container here. One is this container, okay, and another one is this only, okay, another one is this. So, same liquid is there in both, same liquid, okay, liquid is same. So, its surface energy and its surface energy will be same or different? Different. Whose energy is more? Its energy is more. Why? Because there are more particles in this, more particles. So, that's why its energy will be more. Or you can say, because the surface area is more, surface tension will be same because the same liquid, okay. Surface tension here and here is same, St, here and here also St, but here area is more, so that's why surface energy is more. That way also we can say, or in another way, as I told you, here more particles are there, so actually surface energy will be energy of all those particles. So since here more particles, more surface energy as compared to this one. Okay. All right. Then what else we can say about surface tension and surface energy here? Okay. Right. So surface energy we said already. Surface energy is surface tension into surface area. Now surface area, always remember, it is area of free surface. Area of free surface. Okay. Now let's talk about two things. One is a drop and one is a bubble. Okay. So when we talk about a drop, this is the drop, a water drop. Okay. Now, how many free surfaces it has? Only one surface. Okay. And here are those particles which are on the free surface. So, if surface energy of this drop, we have to write. Okay. What do you write? Suppose its radius is r. Okay. Surface energy. We will write surface tension into 4 pi r square. Remember, it's a drop. Don't write it as pi r square. It's a drop. It's spherical. Okay. Same way bubble. Okay. Bubble. So how is bubble here now? Okay. Bubble will be like this. Okay, bubble will be like this. So bubble has two surfaces. Bubble has two surfaces, two free surfaces. Okay. So when it has two free surfaces, then free particles will be here also. Okay, here also, and here also. So in this one surface energy, will be associated with both surfaces. In this one surface energy is going to be surface tension into 2, if suppose its radius is also r, 4 pi r square. That will become surface tension into 8 pi r square. In what? In bubble. So bubble is there, no? There. Surface tension into 8 pi r square for bubble and surface tension into 4 pi r square for drop. Okay. Any film is there? Film obviously will be associated with soap only. So there also there are two surfaces. Remember that. Okay. All right. Okay. There is a question here now. The question asks you, what is the work done and blowing a soap bubble such that its diameter increases from D to D. Now, what it's doing, it's increasing the area of the bubble. So, when you increase the area of the bubble, who has to work? We have to work. How to find it? Here, work done will be surface tension into change in area. Okay. What is work done? Surface tension into change in area. Surface tension into change in area. So, fine. Surface tension is like this. Then what it says? Initial diameter is D, final is capital D. And since it's soap bubble, how many surfaces it has? 2. So let's multiply it directly. And then we'll talk about change in area. So initial area 4 pi r square. But r is what here? Given in terms of D. So r means D by 2. This is initial area. Final area 4 pi again D by 2 whole square. Okay, put it here. So 4 pi you can take common. Then what you have? D square by 4 minus D square by 4. Right? So what we got? Surface tension into 2 into 4 pi. Take out this 4 also outside. Then what we have? D square minus D square. 4 and 4 cancel. So surface tension into 2 pi D square minus D square. This is work done. That many joule. Right? Okay. Then one more question is there for you. Okay. Energy needed in breaking a drop of radius r into n drops of radius r. Now again what we have to see is when you say energy needed. So energy means it's a form of work done only. We have studied already work done, work energy theorem, work can be converted into energy. So here also we are talking about surface tension into change in area. Okay, let's see. Okay, so here it is. So energy needed, I am just writing here first surface tension into change in area. We'll see what is happening. What he says, energy needed breaking a drop. So one big drop is there. One big drop of radius r is there. And then you are breaking into n small drops. Okay, n small drops of radius r. So fine, there is a small drop of radius small r. Okay, so what relation we can have between them? That whatever is the volume of the drop, from that volume only n drops are made. So that means volume of this will be equal to n times the volume of this. Correct? Okay. So 4 by 3 pi capital R cube equal to n into 4 by 3 pi small r cube. So 4 by 3 pi, 4 by 3 pi cancel. So r cube equal to n r cube. Let's come here. Surface tension is surface tension only into final area minus initial area. Okay, so surface tension here into final means what? There are how many drops? N. So n into 4 pi small r square minus initially one drop. So 4 pi capital R square. 4 pi you take out, surface tension into 4 pi. Now n into small r. Now small r is what you can see? R equal to n to the power 1 by 3 r. Cubic root I have taken. Okay. R equal to n to the power 1 by 3 r. So small r value we can write r by n to the power 1 by 3. So r by n to the power 1 by 3 square minus r square. So r square you can take outside. Surface tension into 4 pi r square. N by n to the power 2 by 3. Square is there. N to the power 2 by 3. So n by n to the power 2 by 3 will give you n to the power 1 by 3 minus 1. N to the power 1 by 3 minus 1. So this much energy is required. Clear? This much energy is required to break it into n small drops. What you are doing? when you are converting into n small drops, you are increasing the area. You increase the area. See, r has become n to the power 1 by 3r. If n is 2 also, okay, that means it's positive. So what's coming? If this is 2 also, 2 to the power 1 by 3 minus 1, that means it is positive i. So that means energy is required. Okay, energy needed in breaking the drop. Okay, fine. Then what? Now this is a question on film. Rectangular film of liquid is extended from 4 centimeter into 2 centimeter to 5 centimeter into 4 centimeter. If the work is this much, surface tension. Okay. Now see, in the previous question, it was a drop. So I didn't say you that there are two surfaces. Remember, if it's a bubble, you have to take two surfaces. Okay. Right. Rectangular film of liquid is extended from 4 into 2 to 5 into 4. Or 5 into 4. If the work is 6 into 10 to the minus 4, surface tension. Okay, this is a film. Film means against two surfaces are there, remember. What we have to do? Surface tension, we have to. Same thing, work done is equal to surface tension into change in area. Work is given. Surface tension we have to find. Change in area also given, but remember two surfaces. So, okay, it's 20 centimeter square and that is 8 centimeter square. 20 minus 8 into 10 to the power minus 4 into 2. Why? Because two surfaces. That is it. 10 to the power minus 4, 10 to the power minus 4 cancelled. Now this is 6 equal to surface tension into 12 into 2. The surface tension is 6 by 24. That is 0.25. What is the unit of surface tension? We didn't discuss so far, right? So it's energy by area, surface energy by area, surface area. Energy means joule per meter square. Okay, so joule per meter square. Okay, so that's all for today. What you can do is, I am sharing this with you. Just take its code. See, I'm trying it. Possibly it will work. It's not coming. Okay, we'll see it tomorrow. Okay, because I was trying it. If this I share with you, you can scan it, but directly whatever I have done here, that will come. It came. Okay. So now, if you are scanning it, okay, whatever I have done on the board, it will come to your mobile immediately. Okay. So scan it, and that's it. That's it for today. Okay. See you tomorrow. Bye bye.